Mm.
So, good evening, everyone. I welcome you all to this. There is a time here. It should be 8. So, I welcome you all to this week 8 live session on the course Deep Learning. This course is offered by Professor Praveer Kumar Biswas, who is a professor in the Department of Electronics and Electrical Communication Engineering, IIT Kharagpur, and myself, Arka. I will be your NPTEL PMRFTA for this course in this semester. Today we'll start with a Python coding session. So in that Python coding session, we'll be actually talking about the autoencoders. So I will show you three different demonstrations of autoencoder. So one of the autoencoder is basically the ANN based autoencoder. So what do I mean by ANN based autoencoder is actually you already have seen that MLPNN, which is basically multilayer perceptron. So multilayer perceptron is nothing but it contains different numbers of neurons in each and every layer. So it's basically an 1D array. So using the concept of multilayer perceptron, or basically which is also known as artificial neural network, basic artificial neural network, will be constructing the autoencoder. So that is one of the variety of the autoencoder. Second one that I will show is basically, so you already have seen what is basically called a convolution operation, and as well as you are also been told about the variety of convolutional neural networks. So such as AlexNet, such as VGG16, ResNet, and probably GoogleNet as well. So all these networks, basically the main heart of the building block is basically the convolution layer. So we'll also try to construct the autoencoder out of that convolutional neural network scheme. So that is basically called an conv autoencoder. So convolutional autoencoder, convolutional A. And you guys already seen that the application of one of the autoencoder or a variety of an autoencoder is basically uh, denoising autoencoder. Denoising autoencoder. So we'll also uh, construct a denoising autoencoder. So in case of a denoising autoencoder, the input is basically parted up with different sort of noises, and then at the output end, we try to create a cleaner version of the input. So which basically gives you the flavor of denoising application. So we'll be using again the MNIST digit dataset that is available in TensorFlow and Keras. And we'll also see a short demonstration of PCA, that is principal component analysis. Along with that, along with that, you guys already been seen that one of the CNN networks, very preliminary CNN network was LeNet5. So I will try to construct a convolutional neural network as well, which is basically LeNet5 architecture. And upon devising the LeNet architecture, you will get a knowledge that how to write a CNN network by your own. So you can construct several other neural networks such as AlexNet, VGG, ResNet by your own. So the LeNet I will show, and rest of the neural networks you can by yourself you can design it. And after doing this Python session, we will take up some basic questions for week 8 practice questions. So let us then start the coding session. So I will be using the uh, Google Colab platform, which I had used earlier as well. So I guess someone is trying to join. Let me see. Okay, so we'll start with the autoencoder versus PCA code snippet. So again, I will be uploading this particular uh, code or this particular IPyInv file into my GitHub account. So you can just go to my GitHub account and then there will be a button run on Colab. So if you press that button, it will directly head you to your own Colab platform. So then you can run all the codes by your own as well. So for the time being, I have not uploaded there yet. So after this class finishes, I will be uploading the code there in the in my website itself. So let us start the implementation. So can you confirm whether the font is visible now, or should I maximize it again? Is it visible to you?
Yes, sir. Visible. Yes.
Okay, okay. So I will walk you through all the codes that I have written. So this part basically shows that I am importing different sort of libraries. So as I already have told that I will be using MNIST dataset. So over here, what I am doing is I will be referring to the dataset from the Keras package or the Keras distribution. So that is why I have written import Keras. And then from Keras.dataset, I already have said that Keras have basically different sort of datasets stored inside its package. So inside that package, there is a container dataset, and from the dataset, I will be using MNIST only. So therefore, I have written from Keras.dataset import MNIST. After that, whatever array will be generated will be doing some sort of array operation on top of the variables. So that is why I have imported the NumPy library. So that is why I have written import NumPy as NP. Then it is time to extract all the data, basically training and testing data from the MNIST dataset. So that is why I have written two sort of structure, which basically gives you the flavor of xtrain, ytrain. So this basically gives you the training set, and xtest, ytest. This is the testing data, and this is the testing level. So equal to mnist.load data. So which basically what it will do, it will load the mnist data set and then it will extract the files according to their their individual location. For example, training data will come into the xtrain, training label will come into ytrain, and likewise we can see that testing data, testing variables have already been declared on top of which all the data will come uh, from the mnist.load data. So let us run this one. So one thing that you have to remember is that when you'll be using Google Colab, let's say for deep learning application, so there are two sort of there are two sort of hardware that you can employ to run your deep learning application. One is basically the normal hardware, that is CPU. So in CPU, you do not have the paradigm of what you call parallel processing and multi-thread version and all. So CPU is slower as far as deep learning application is being concerned, because in case of deep learning is data hungry. So you need to process a huge amount of data in each and every epoch. So therefore, it is advised to use GPU instead of using CPU, because in case of GPU, depending on what GPU you are using, so that will have several threads. So it will have the paradigm of parallel processing. So it will help in computation. It will help in computing all the operations in a faster manner rather than what was there in case of a CPU based machine. And there is another version of hardware that is provided by Google Colab, that is called TPU, that is called Tensor Processing Unit. That is also specialized for deep learning and machine learning application, because in case of deep learning and machine learning, you will be dealing with the tensors. So what do I mean by tensor? So there are one sort of data type, for example, vector. So vector is an 1D array. Then you got a 2D matrix. So you got a 2D data structure that is called a matrix, which will be of shape m by n. Vector was m cross n, m cross 1 because it's an one-dimensional data. Then matrix is a two-dimensional data, which is basically m cross n. Now, when you have a stack of two-dimensional data or multi-dimensional data, so that is basically called a tensor. So one example of a tensor shape would be, let's say, 60,000 cross 28 cross 28 cross 3. So now you can see, instead of having m by n, now you have 60,000 cross 28 cross 28 by 3. That means it's a five-dimensional data. So these sort of five-dimensional data or higher dimensional data are basically referred as a tensor. So to process those data types, basically they do have you can either use GPU or you can use TPU. So there are three types of GPUs are there: T4 GPU, A100, and B100. So over here, you will see with the normal version of Google Colab, you will be accessing either TPU or GPU, T4 GPU or TPU. However, if you purchase the Colab Pro or Colab Pro Plus version, so then you will get these two GPU. And let me tell you, these two GPU are very fast. They have huge computational capability. So as because this is my personal account, I do not have the Colab Pro Plus version over here. So I will be using simple GPU T4 one. So just tap here and save it. Now you can start running the codes. So it will take some time to connect. So over here you can see that connecting and green dot is there. That means it has been allocated with all the resources, and now it will start executing the code. All the data that have been there have been downloaded. Now let us just uh, 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 do some data pre-processing. So let me go to the next page and show you. So can any one of you tell me that what is the shape of the MNIST digit datasets images? So MNIST digit dataset comprises the handwritten digits, and we have also seen from previous live coding session. So we have loaded those data sets and visualized. We have also visualized them. So what is the shape of the images? Handwritten digit images. Anyone? Okay, so the shape of the image is basically 28 cross 28. So you have an image size of 28 cross 28. But in the case of an autoencoder, you have seen the autoencoders are like this. You have the input data in this particular form. So this is, let's say, the encoder layers, and then the decoder layers are placed like this. So decoder will basically generate back your input, and over here also the data are like this. Okay. So what it will do, so this particular part is basically called the encoder, and this part is basically called the decoder. So let's say you have n number of input neurons. So this is x1, this is x2, dot 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 dot. This is xn. And how many neurons you will have in the output? Anyone? How many neurons will be there in case of an autoencoder? If you have n number of input entries in the autoencoder, so how many output nodes you'll be having?
In number of output.
Yeah, so you'll get an n number of output. So let's say, let me write it as x1 hat, x2 hat, dot 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 xn hat. So given this kind of architecture, so you can see that your input image is a two-dimensional image, which is of shape 28 cross 28. However, in case of an autoencoder, basic autoencoder, you can see that the data that basically the autoencoder receives, it's a 1D data. So if I write the dimensionality in terms of vector dimension, so it will be R of n cross 1. So you can see that you have to so over here your data is two-dimensional, but your autoencoder takes an 1D data. So what you have to do is basically you have to convert your two-dimensional data into an one-dimensional data. And how will you do it? If you have to convert this two-dimensional data into an one-dimensional data, how will you do it? So what you will do is basically you will stack the columns one after another. So let's say, so you have 28 columns. So let's say this is first column, this is second column, third column, dot dot 28 column. So what you will do, you will append each and every column one after another. So this is first column, then this is second column, and likewise it will continue to the last column. So over here, so you will get from a 1D data, you will get a, sorry, from a 2D two-dimensional data, you will get a one-dimensional representation. So this one-dimensional representation will be of size how much? So what will be the size of this particular 1D data generated from the 2D image? Is anyone? So this will be, so let's say you have 28 data over here. You have 28 number of columns and 28 number of rows. So each column will have 28 entries. And you are stacking all these 28 entries one after another. So first column, first one will have 28 values, second one will also have 28 values. And how many such sort of columns you are appending? A total of 28. So it will be of size 784 cross 1. So now you can see from this 28 cross 28 data, you have got a one-dimensional data of 784 cross 1. So now this 784 cross 1 data, you can feed it to the network, to the autoencoder neural network, and then you can get it done by encoding and decoding and all. So this is the main fundamental thing that you have to remember, that your autoencoder, if it is made of a multi-layer perceptron network, so over there, you cannot feed a two-dimensional data directly. What you have to do is basically you have to flatten the data, or you have to create a one-dimensional data representation, and then you can feed it to the neural network. So before feeding to the neural network, we have to reshape the data as per the requirement. So that is what we are doing over here. So you can see that x train is equals to np dot reshape. So what we are reshaping? We are reshaping the training data itself, and then what will be the dimension? The dimension will be, we have total number of 60,000 data in the input. Total number of 6,000 sample images in the training set. And instead of 28 by 28, what we need is basically in 1D data, which is of 784. So that is why I have written 784. So test data as well, we have to reshape it into a 1D array. So therefore, I have written np.reshape x test, comma 10,000, 784. So 10,000 is basically what is the shape, what is the number of images in the test set that is present here. After that, we are actually normalizing the pixel values by dividing it by 255. So it will normalize all these values in between 0 to 1. So that is what we are doing, the same thing in the case of X tests as well. And then we are printing the shapes. So if I run this, you will get a shape of 60,000 cross 784 and 10,000 cross 784. So this is for the, so there is a typo over here. So let me write test. So the training data is of shape 60,000 cross 784 and the testing data is of 10,000 cross 784. So we have flattened the data from the two-dimensional data representation. Now our job is to create a autoencoder. So in the last class, I have told you that uh, someone has asked that what is the meaning of deep autoencoder and what is the meaning of a shallow autoencoder. So shallow autoencoder is basically, uh, let's say you have an input layer and autoencoder will have the output layer of shapes of same shape. So over here, let's say in the input you have n number of data points. In the decoder output layer also you will have n number of what you call the output neurons. Now in the hidden layer or the encoder decoder layer, if you have very small number of, if you have very lesser number of intermediate layers or the hidden layers, so that sort of neural network architectures are called the shallow neural network architecture. For example, you can see that you have the input layer over here. So this is the input layer, this is the output layer, and this is the bottleneck layer. This is the bottleneck layer. And you just have a single hidden layer to encode your encode the all data. So you can see, so this is the encoder section and this is the decoder section. Okay. So now you can see that you are employing the single layer to encode all your data, and then subsequently you are passing this encoded data to the decoder to get it reconstructed again. So over here, as you can see that as your number of hidden layers is very much less, so these sort of neural networks are called shallow neural network. And in our first exercise, we'll be trying to construct a shallow neural network itself. So the dimension of the neural network that we are considering for this particular application is basically is basically uh, so the input layer will have 784. So the input layer is having 784 neurons, and as well as the output layer will also have 784 neurons, and the hidden layer or the bottleneck layer will have 100 neurons. So we'll be constructing an autoencoder of this sort, 784. So this data will be encoded to a 100-dimensional data representation, and then this 100-dimensional data representation will be fed to the decode part, which will regenerate or reconstruct the input as again. So the output will have 784 number of neurons. So that is what we are now going to construct over here. So the encoding dimension is 100. Now what we need is basically to construct a model or a deep learning model from Keras.model. So Keras has different packages. So if you get time, then you can search for different different containers that basically Keras contains. So models is basically one such container inside the Keras distribution. So from the models, you can import models. So this will help in constructing all the layers that you've been using to create a deep learning architecture. So Thereafter, you have from Keras.layer import, input, and dense. So dense is basically your multi-layer perceptron. Input is basically when you feed any sort of input in a deep learning architecture, you need to declare the shape. Now that shape, it will come into this particular into this particular command. That input will have an argument of shape, how of the dimension that we've been declaring. So over here you can see that your input image is equals to input. So I am referring to this particular layer. So in a deep learning architecture, you will have an input layer which has a specified dimension. So over here, our input image is basically the first layer, which has the dimension of 784 declared over in this particular method. That input which receives an argument of shape equals to 784 comma. If you just leave it over here, nothing is there. So the model will code will basically observe that there is one is there. If you just keep it empty, then the command will by default it will put a one over there. So this is a common practice to keep it blank. Then what you have is basically you need to encode the 784 dimensional data into 100 dimensional data. So therefore I have written down the comment as well. So if you get time again, you can read it along while basically resimulating the code. So encoded is equals to dense encoding dimension comma activation value. So what it basically does is, and it receives an data that is basically an input image. So if I just show you in terms of the layer, so what we are doing is basically, so we have already declared the input layer. So this is the input layer. We have declared through input shape equals to 784 comma blank. So this instantiates this particular input layer. Now our job is to instantiate the bottleneck layer or the hidden layer. So I have named this particular layer as encoded. So this encoded, how I am declaring it is, so encoded is equals to dense. So dense is basically the your multi-layer perceptron. So dense. So you need to specify that how many neurons will be there. So that is why I have written 100, as because already I have shown that will be encoding all the 784 dimensional data into 100 dimensional data. So over here dense equals dense within bracket 100 comma. So you need to put a activation function over there. In case of deep learning, you already have seen that deep learning methods, what it basically does is it aggregates the data from the previous layer and then it passes the data through a activation function. So that is why I am writing a activation function that is ReLU. And ReLU also you have seen that what basically ReLU means. So this particular line will instantiate this particular uh, layer over there. So encoded is equals to dense encoding dimension. I have written over here with 100 and then activation is equals to ReLU. Now what it will take as it as an input. So first you are feeding the input data over here. Then the input data will be passed to this particular encoding layer. So let's say these are the neurons of the input layer. So this will be like this. So all the data will be connected. So as you know that how the data basically connects in the neural network architecture. So every neuron from the previous layer is connected to every possible neuron in the next layer. So over here, this input data will be passed to this particular encoded layer. So that is why after you declare the shape of the encoding layer, so you need to put a input to this particular layer. So that is basically your input image. So what we have declared in the first line. Now what you have to do, you need to create a decoder layer. So that is why I have probably named it as decoded or something. Let me just see and then I will illustrate that. So yes, so I have written the decoded, and the decoded will also have a dense layer. So the decoded, so this is basically the output layer of the decoder. So this is, I have named it as decoded. So the decoded layer will also have 784 number of neurons. That is why I have written over here decoded is equals to dense. We need a dense layer to create this decoded layer. And first we need to initialize the uh, shape of the this particular dense layer. So it will have 784 neurons over there, and then you can pass it through an activation function. It basically depends on what sort of application you want over there, and then you pass an input to this particular layer. So what will be the input of this particular layer? Anyone? By you need to first visualize the thing, otherwise just showing all these applications will not be able to understand. So you have this decoding layer. So what is the input of this particular decoding layer? So what is the input to this decoding layer? Okay, so as you see that from here, first you are feeding the data, then the data is going to this encoding layer. Now whatever data comes from this encoded layer, it will be passed to this decoding layer. So it will be encoded. And then over here, as because we'll be generating the binary images, so therefore either we need 0 and 1, so you can put sigmoid as the activation. So after assembling all the layers, so you can see we have constructed input layer, encoding layer, and decoding layer. Now you can construct all these layers to create a model. So first you instantiate all the layers, and then you assemble all the layers to construct a model. So over here you can see that I have instantiated the input layer, encoding layer, decoding layer. Now you can create a model, and I have named it as autoencoder equal to model, so that we have already instantiated from the Keras package. The model, it will take the input layer and the output layer. So our input layer is basically the input image, and the output layer is basically the decoded. So the model will get to know that, okay, if this is the input and if this is the output, what sort of intermediate operations are being happening, that will basically taken care of by the Keras package itself. So let me just instantiate it. Now you can actually even check the summary of the model. So over here you can write autoencoder dot summary. So it will give you a nice summary that what sort of tensor operations that is basically doing. So you can see the input layer, which is of shape 784. Then you have dense layer, which is of shape 100, and again a dense layer, which we have named it as decoded, which also has 784 number of neurons. And you can see this is basically the parameter. So what sort of parameters are basically meant by this? So throughout the quiz 4, 5, 6, you have done several numericals which basically deals with extraction of how total number of trainable parameters. So these are the total number of trainable parameters that you referred in the question. So you can re-verify, but over here you have to cautious about in the quiz question, they always say that there is no bias. However, in deep learning, there will be obviously bias terms are there. So they have considered both the bias as well as the weight terms. So you can re-verify all the values over here by calculating the weight by yourself. So this is a task to you. So you can layer wise you can check, and you can just calculate the values, and then even you can see that whether you are getting it correct or not. Okay. Okay. Uh, so if you construct this autoencoder, so the autoencoder is meant by this whole thing. And in the test time, so please tell me, in the test time, do we need the decoder part? In case of an autoencoder, while doing the inference, do we need the decoder part? Yes, anyone? Okay, so if you have seen the lecture, so you have seen that while training an autoencoder model, you need the encoder and decoder. Decoder basically tries to regenerate the input that you have fed to the network, and as because your main aim is basically to get the hidden representation at the bottleneck layer, so you need some sort of loss function that has to be carried from the input to output to get it trained in an end-to-end fashion. So over there we use our MAC loss or different sort of L1 or L2 loss over there. And that is why you need a decoder, as because you're reconstructing the image, and your basically expectation is basically to get the perfect reconstruction over there. So that is why you need the decoder layer while training. Now, upon the training is done, now what was your aim is basically to get the hidden representation. So now to get the hidden representation, you just need the encoder part only after training the model. So after training, you just chop off this particular decoder section, and this part is basically called the encoder model, which you need while testing this particular model. So now here I have declared the encoder model like this. So the encoder is equal to model. It will receive the input image, and what is the output now? So the output is basically the encoded vector. So this is basically generates the encoder model. So you have, in case of an autoencoder, you have two sort of models. One is basically the full autoencoder model, which basically employs the encoder decoder architecture to create a faithful training process. That means, given a sort of image, you need to get it perfect reconstruction back at the decoder set. However, while doing the inference, you just need the encoder part, not the decoder part. So that is why we have chopped up the decoder part over there. So now you need to compile your autoencoder model. So for compilation, I have used an optimizer, Adam. So this optimizer thing will come into the next week probably. So till then, just consider it as a argument. And loss, already we have seen that in case of numerical examples, we use the squared error. However, as because we have several sort of training instances, so over here we have incorporated the mean square error loss. So in a batch, it will basically calculate the squared errors, and then it will take the mean out of all this. So Now after compilation, now you need to train the model. So to train any model, the function is basically called the fit function. The fit function will take uh, the training data. So you need xtrain and xtrain over here, as because this is an unsupervised learning mechanism. Autoencoder is an unsupervised learning. You don't need the training level over there. And then you need to write down the epochs. So how many number of epochs that you want. Then you'll the autoencoder will be updated using the gradient descent tool, and we have seen that there are three different variety of gradient descent applications. So one is basically the batch gradient descent, which basically uses the full batch data. One is the stochastic gradient descent. So stochastic gradient descent, for each and every sample, the loss will be calculated and the weights will be updated. We have seen that the training process becomes very noisy over there. And the last option that we have is basically the mini batch gradient descent. So we basically declared a subset of the whole training batch, and for that particular subset, the loss will be calculated, and then the weights will be updated. So over here, to employ the mini batch gradient descent, we have constructed a batch size of 128. So that means at a time we'll be feeding 128 number of data over there into the model, and then the model will be updated accordingly using a gradient descent approach. After that, we have written shuffle. That means each and every, while doing the epochs or the iteration, so data will be shuffled in each and every iteration. And then we also have to validate the model. So for validation, we have used the test data. So now let us start the training process of the autoencoder. So it will take a couple of minutes to run. So over here, I have just used 20 epochs. So you can increase the number of epochs, and then you can see that what is basically the response. So for the illustration purpose, I just have taken it 20. Now you can see that 17 epoch has been covered. Okay. So now let us just plot the curve. So you can see that we are plotting the training loss versus validation loss. So you can see that our model basically achieves very low value of loss within a very few epochs. So that means 20 epochs is quite sufficient to get a good model representation. So from this particular response from the training and validation, we can see that there is no overfitting is there. So that is basically a main job in a deep learning architecture, that we basically try to uh, um, get rid of the overfitting issue. So over here, we can see that there is no overfitting. So that means we are safe, at least on a safe side, to call it a good model. So let us now use the test data to predict the images. And now someone's mic is on. Okay. So now we'll see that how our autoencoder has uh, reconstructed all the images while training. So you give an input image, so that is your X. So if I go to the slide again, so in an autoencoder, you feed an input image X, you get a output X hat, and your job is basically to reduce the uh, uh, distance between X and X hat. So MSE, mean squared error, X comma X hat should be minimized. So if I just write in terms of an optimization equation, so it will be argmin, uh, and the variables would be weights and biases of the model of the encoder and decoder as both. So argmin of the weights and biases will be optimized, and the objective function is basically the MSE, mean square error, between the input image and the reconstructed image over there. So now, if your model is very much well trained or perfectly trained, your predicted images will be as close as to the original input image. So now we'll be seeing the images that you feed as an input and the images that we get from the autoencoder output. So over here, that is what I have written. So from the command, from the print lines, you can see this is the test data as input, and this is the reconstructed image. So let us just see what is the performance. As well, you can get the latent representation. So our main job is basically the to get a latent representation. So latent representation will come from this encoding layer. So over here, the encoding layer is there. So this encoding layer will give you the latent representation. So this latent representation is of how much dimension? This is of 100 dimensional data. So over here, you will get a 100 dimensional data. So if I just show you the shape, so the latent representation will have 100 cross 1 shape. Dot shape. So you have total 10,000 data in the test set. So it will be 10,000 comma 100, because each of them are 100 cross 1 and you have 10,000 such images, so it will be 10,000 cross 100. And if you just want to visualize it in terms of an image, so over here you can see that what sort of representations you are getting, and these kind of representations you can further use for your own classification task or regression task in the later on stage after chopping of the decoder section. Okay. So the next use case that we'll see is basically a deep autoencoder. So the deep autoencoder, instead of having a single hidden layer, now we'll have 3 hidden layers over here. So you can see that the first hidden layer that it has of 120. So the first layer is basically the input image layer. Second layer is basically the encoded layer over here. Third layer is also a dense layer of 64 neurons. Fourth layer is a dense layer of 32 neurons. So over here, the encoded section is done. Now you try to reconstruct back using decoding mechanism. So from 32, you now need to create the 64. From 64, now you need to create 128. And from 128, you try to reconstruct a dense layer of 784 neurons. So that is your input image dimension. And at the output, you can see the activation function is sigmoid over here. And in the intermediate hidden layer, we have kept the ReLU activation to alleviate the gradient vanishing gradient problem over there. So now just use this particular model method to generate the autoencoder as well as generate the encoder model. So now you
Sir,
can see the
question.
summary as well. Yes.
Sir, can you just scroll up?
Yeah, yeah.
The deep autoencoder. You have declared all the
Huh,
AI. No, not this one. Just a little bit down.
it's a little bit down.
Yeah. So this the second set you have decoded equal to, right, like 64, 128, and 784. Huh? So the first 64
Yeah,
should
yeah.
be yeah, decoded, right? The
Huh,
first
so this is decoder.
yeah,
This is
dense
decoder. So what?
64 activation relu the last yeah, the one should
So
be decoded.
this
Yeah.
no, no. So over here, what is basically, this is the input to the model. This is the input to the layer. So over here you can see, if I go to the slide again, so let me just create another dummy page. Yeah, if I show you over here, so let's say this is your input layer, this is 784. Now you have first encoder layer 128, the second encoder layer 64, and the last encoder layer is 32. Now what you are writing over here, for example, for this particular layer, you are writing dense, and this layer is, let's say, input underscore image. So dense for this particular layer, this is dense 128. Then within invited comma, so this will be relu. And now you need to write the input to this particular layer. So what is the input? From this particular layer, whatever output comes, that will be fed as an input to this particular layer. So this, whatever output comes from this input image, so that will be fed to this particular layer. So I can write it as input underscore image. Similarly, if I just write it, so it will be dense. The neuron shape will be 64, comma, this will be ReLU. Now again, you need to write the input to this particular layer. So what will be the input? Whatever output comes from this 128 dimensional data, so that will be fed to this particular network. So that is why you write it over here encoded. Same thing happens over here in this particular layer. So it will be again dense 32, ReLU, and then what will be the input to this particular layer? So that is basically the encoded output from the 64 dimensional data. So I have named all these as encoded only. So I have written encoded. Now the decoder part comes. So if I just show you over here, so this was the 32 encoding layer. So now the decoder part will come. So this is the first decoder layer, so which is of shape 64. Now, if I write the code for this one, so it will be dense. The number of neurons it will have is 64 over here. You write 64, and then you write the activation function ReLU. Now, what will be the input to this? What will be the input to this layer?
This will be 32. Yeah, 30.
So the encoding of this 32 dimensional layer. So over here, so it will be encoded only. Because over here, whatever data was coming from the encoding layer, I named all of them as encoded. So from this 32 dimensional layer, we got again the encoded. So the variable name is encoded. So that is why we are writing encoded. In case of second decoder layer, so now the decoded has been started. So this second decoder layer, let's say this is of 128 dimension. So it will be dense 128 ReLU, and then now you need to feed a input to this particular layer. So now the decoder has been started. So whatever data comes out from the 64 dimensional data, so that will be fed to this particular 128 dimensional layer. So what is the data that is coming out from the 64 dimensional data? That is basically the decoded output. So that is why I write decode.
Okay, thank you. Thank you.
Okay. So again, you can see the summary over here. So you can see that it starts from 784, goes to 128, 64, 32, and then you try to reconstruct it back. So by 64, 128, and followed by that 784. So along with that, you can see the total number of parameter layer wise. And I request you all to recalculate all these parameters by yourself, just considering the bias term as well. So you will get to know that how the deep learning model, the total number of parameter can be constructed from the deep learning model architecture itself. And while you sum this all, so you will receive the total number of parameters over here. So there are two sorts of parameters are there in a deep learning model. The one is trainable parameter, one is non-trainable parameter. So non-trainable parameter you will see in transfer learning application, but today let us just focus on the trainable parameter only. So in case of transfer learning application, there you will see sort of non-trainable parameters and trainable parameters uh, uh, representations of that. So over here, non-trainable parameter is equals to 0. So again, you can train your model over here. So I am not training the model again because it will take time. So let me just walk you through, and you can re-simulate everything by yourself at your terminal. So you just press the run button and it will start running. But let me just skip this part because it will anyway take time. So you can see that number of epoch is 50. So it will take a substantial amount of time to run. So to train a model, first you need to compile the model. So autoencoder.compile. So you can use an optimizer. You can use Adam, Adagrad. Then there is another momentum optimizer, etc. So all these things you will see in the next week. And you can declare a loss function. You can use MSE. You can use MAE. So MAE is basically mean absolute error or the L1 distance or Manhattan distance. Then you can use autoencoder.fit. So the fit function will basically start training the model. So to train the model, you need to pass the training data x10, x10, number of epochs is 50. To employ the mini batch gradient descent, the batch size I have taken as 128. So all these values, epoch 50, batch size, all these are called the hyperparameter of the model. So you can plug and play with different values and see that for which value you are getting the highest result. Then this shuffle is true because at the training time we'll be shuffling the data for each and every epoch. And while training the model, we need to validate the model as well. So that is why I have used the validation data at the X-test data. So you can train it by yourself, and the same thing I have did over here as well is basically to show you that what is the input data, test input data, and the reconstructed images from the what you call uh, deep autoencoder model. So it will again show you that what sort of data you are giving to the input layer and what sort of data you are getting back from the output layer of the autoencoder model. So you can just train the model and you can take the output at your side. Okay, so we have covered the shallow autoencoder, the deep autoencoder, but however, in all these cases, we have used simple dense layer based autoencoder. We have not talked about CNN based autoencoder. So in this particular application, in case of denoising autoencoder, I thought that we can use the convolutional autoencoder as because you guys already know what is convolution and how the convolution neural network works. So in case of denoising autoencoder, what we do is basically we feed the noisy data to the autoencoder by some sort of noise insertion mechanism. So let's say this is the autoencoder input part, this is the encoder, and this is the decoder one. And if this is an image, you add noise to that and you get a noisy version or perturbed version of this input. This I name it as noisy image, and you feed this noisy image to this encoder part. It will be fed to the encoder section, and then in the bottleneck layer it will get a hidden representation. Then it will be fed to the decoder part. So you had, in terms of mathematics, you had x, you add a noise eta over here, and you get a noisy image. So let's say this is x noisy. And at the output side, what you want is basically to get back the clean version. So then only you will get a denoising effect. So given the noisy image, you need to get back a denoised version. So that means your expectation is to get a x hat, and the loss function will be MAC x comma x hat, not between x noisy and x hat. your expectation is to get back the clean version. So what is the clean image? So this is the clean image. So you can take MAC between X and X hat. So that X hat is basically the model prediction and X is basically the clean data that you basically partner up with different sort of noise. It could be a salt pepper noise. It could be AWGN. So the AWGN is basically an additive white Gaussian noise. It could be pink noise. So in our case, we have used the Gaussian noise only. So let me just walk you through the code part. So this is your X train np.reshape. So in case of convolutional autoencoder, as because we are using convolution mechanism, so now you don't need you don't have to basically uh, uh, flatten the data. So rather you can use the 28 by 28 by 1 dimension itself. So I am again reshaping the data. So you can see that shape is currently 60,000 cross 784. So 784 basically gives you the one dimensional data. However, uh, now we can use the two dimensional data, which is of form 28 by 28 and 1. 1 basically shows you the number of channels present in the data itself. And again, in the test data as well, we are doing the reshape version. So from the one dimensional data, we are creating the two dimensional data of 28 plus 28. And then we are using a noise factor of 0.5. So this noise factor will basically give you that what at what intensity level you are basically trying to add the noise. So we are using the np.random.normal. So np.random.normal is basically refers to the normal distribution or the Gaussian distribution with zero mean and unity variance. So over here, so 0 and 1 basically gives you the zero mean unity variance representations. And you need to specify the size as well, that how much size of noise have to be generated. So that will be of equal shape of X train. And then we are clipping the input representation just to normalize the thing, because in case of deep learning, you'll see in the next week as well that what is the role of normalization. So you'll see instance normalization, batch normalization. So there is a phenomena called covariate shift. Normalization helps to reduce the covariate shift over there. Now it is time to show you that how we have perturbed the input data. So over here, you can see that we have perturbed the data like this. You fed the data over here, and this is the sort of perturbed version that we get from the input data. Okay. Now, after doing the noise perturbation, as because we are using the convolutional mechanism to create the autoencoder, so we need the following layers. So one is the input layer, dense layer, conv2D. So conv2D will give you the convolutional mechanism, and you have seen that in case of convolutional neural network, the subsampling layers is also used. So that is basically called the max pooling layer. Or instead of max pooling, you can use several other sort of subsampling layer. That could be, let's say, average pooling. That could be uh, mm, sum based pooling, etc. Okay. Now, over here, I have written that from Keras.models equals to import model. So this model, what it will do is basically try to assemble all the layers in the deep learning architecture. And then we have used that from Keras import backend as case. So this basically helps in reinstantiating all the layers over there. Now let us start let us start writing all the layers that we require to construct the autoencoder model. So first layer is what? First layer is the input layer to the deep learning model. So the input layer will have a shape. The image shape is 28 cross 28 cross 1. So that is why I have written input, which receives the argument shape equals to 28 cross 28 cross 1. Then the first decoding layer comes. So the first encoding layer comes. So that is basically I have written over here. X is equals to conv2d. So in case of convolutional layer, first you need to declare the number of filters, how many filters you want. So over here I have written 32. That means I need 32 filters. Then what is the kernel size that you want? So over here I have used 3 by 3 kernel size. That means it will be a square shaped kernel of 9 elements. Then we have activation function over here. So in the neural network architecture, we have used the ReLU activation, and padding, we have considered padding as string. And then we need to feed the input to this particular layer. So input to this particular layer will be input image itself from the previous layer. Then what we'll do, we'll use this subsampling operation. So for using the subsampling operation, we have already said that we'll be using max pooling layer. So the max pooling layer of kernel 2 by 2 and padding is also same. And what is the input that we can feed into this max pooling layer? So from the previous layer, so the previous X output is now fed into this max pooling layer. Same thing happens over here. Again, I use a convolutional layer over there, and then followed by that, I write the encoded output as the max pool output that I have fed from this previous X. Now this is what the encoding, this is where the encoding is done. Now we need to create the decoder part. So this part is basically, if I just write the comment. So this is the encoding part, and this is the encoded vector or the encoded representation, or I can write it as latent representation of the autoencoder. And then over here I can write the decoder part. So now the decoder part starts. Now at the decoder for the first decoder layer, what will be the input to the decoder? So the input to the decoder will be the encoded output. So we can see that we have written over here the encoded part as the input to the next layer. Now again we'll be using conv2d as because this is a convolutional autoencoder. So convolutional autoencoder will have 32 number of filters, 3 by 3 3 by 3 kernel. Activation is ReLU and padding is same. So whatever we have used in the encoder part, so that will be replicating over here one by one in a cascaded format. And in case of encoder part, we see that the dimension gradually reduces as because we are using a notion of under complete autoencoder. Now at the decoder side, we need to regenerate it back. That means we need to, from the downsampled data, we need to upsample the data to get the original dimension. So for that, we are using a upsampling layer. So this upsampling layer is of shape 2 by 2. So that means it will have a kernel, and the kernel will try to regenerate or upsample the data from the smaller or from the encoded data. Then
Sir,
again,
one question.
we'll be using. Yes.
Hello. Sir, during convolution, we apply the filter, right, in order to perform the convolution operation. Okay, so the filters, it could be anything like identity, sharpen, Gaussian, blur. So where we have to mention in the coding that filter?
Okay, so this basically, this is the number of filters and this is the kernel. So let me go to the slide. So let's say this is your image, right? Let's say you have a 3-channel image, and this is of shape, let's say 28 cross 28 cross 3. Now let's say, or let me just start with one-dimensional single channel image, so it will be easier to illustrate. So 28 cross 28 cross 1, and you have 3 cross 3 filters. Someone is trying to join. Okay, so over here you can see 3 cross 3 filters, and how many such filters are there? Let's say you have 32 such filters are there, and stride padding you have considered accordingly. So now your question is this 32 3 cross 3 filters. So you will have these filters which have to be convoluted with this particular image. So you will have total 32 such filters. Now your question is that this could be this filter could be like this filter could be like this filter could be like this, anything, right? But where to mention?
Correct,
So
sir.
so the initialization, generally what the code is basically doing, if you do not specify it, they use random initialization. Now what random initialization? They use the uh, standard normal distribution of zero mean, and initially it was done with unity variance. Now what they do is basically so you have total number of 28 by 28, that means total number of 784 samples in the image. So what they do or is basically n01 by 784. So from this distribution, this is the Gaussian distribution. From this distribution, they randomly pick values and initializes this particular kernel. So initially the kernel could be like this, it could be like this, right? Because it has filled all the values from this random from this distribution randomly. Now upon training, while doing the gradient, while doing the back propagation using gradient descent rule, these weights would be learned, and these weights would be learned in such a manner that the kernels will be able to extract good sort of representation from the input image. Now upon gradient descent based learning, this whole black matrix can get modified to this. So you just you do not instantiate or you do not initialize with this particular filter itself. You initialize with something random, right? And then using the gradient descent rule, your filter gets modified to this sort of representation. That is what gradient descent does. You start with a random data. So in case of gradient descent rule, you write wn plus 1 wn minus eta into de by dw, and this in case of iteration 0, at iteration 0, this w0 is basically comes from random distribution. It basically instantiated with random values, and they can use the standard normal distribution of this sort. And if you try to, yes, please.
That means it will be always randomly initialized only, sir. What
if
if
you
you
do
want
not
like edge detection or any something box blur?
So you can use different sort of different variety of initializers as well. For example, let me show you. So you can use, if you do not specify while writing the code, if you do not specify the initialization, what sort of initialization you want, so it will be random. They will use the standard normal distribution. Otherwise, you can specify the initialization technique. You can write uniform, you can write he, you can write glodot. So these are the defined sort of initializers to initialize this kernel value. So they use different distribution. And now, as you are saying that you just want the age detection. So for that, you have to write your own initializer, which will initialize with uh, these sort of filter representation. So I can uh, suggest you a paper. If you you are a PhD student, right? I hope you are a
Yes, sir.
PhD student.
Yes, sir. Yes, sir.
So as your question is too specific, because you are asking that if you want to instantiate the filter with, let's say, age detection, or let's say something other, or let's say you want your filter to be of this representation, a band pass filter. Instead of using a age detection, means you are trying to extract high frequency information. So let's say instead of high frequency information, let's say your filter would have a band pass characteristic. That means you want something very specific. So you can refer to this paper, SyncNet, SINCNET. So this paper you can refer. So to initialize your weights with something very specialized sort of operation, so you have to write the initializer by your own. Otherwise, if you just want the Keras itself handles the initialization technique, then you will have either standard normal, uniform, key, glodot, etc. Apart from that, if you want to use something very what you call specialized one, let's say like only age detection, only bandpass filter. So for those applications, you need to write your own initializer. I hope this answers your question.
Yes, sir. Yes, sir. I got it. Thank you.
So even I can show you one example. What happened? How we are get rid of this? So if I just cut this particular bar, so will it affect the recording or not? I don't know. If I just cut this one, do you know that if I cut this particular bar, it basically shows that you are sharing the screen and stop sharing? Because if I'm using this one, I'm not able to access the. It is again going to this particular thing. Okay, let me just try one. It is not. Okay, so let me show you SyncNet. SyncNet. SyncNet test. If I yes. So as you are saying that you want something very specialized, let's say age detection or something else. The SyncNet people, what they did is basically yeah, this picture. Just wait for a second. Yes. So you can see these are the weights that they have created. So you can see that initially this is quite low frequency, this is high frequency, this is even more higher frequency. So you can see that they have written their own formula, which basically gives you this specialized weight representation. So in your case, it might be a high frequency edge detection or something else. So for that application, you can write your own equation, which will basically help you generating these sort of specialized functions.
Okay, sir.
Okay.
Bathroom. Then, sir, in coding, after convolution 2D only in there only we have to mention, right, sir?
Yeah, in convolution 2D you can mention. You can mention over here.
Okay, sir.
Then even there are several other. For example, you guys also have read that regularization. So regularization terms can be introduced in the conv layers as well. For example, L2 regularizer, L1 regularizer. So whatever you have learned in machine learning part as well, that you can also employ over here in the deep learning part while declaring the layers. So regularization is one sort of example that you can even include in convolution 2D operation. Okay. After that, you upsample it, and again we have used two convolution layer in the encoding part, so we need to replicate it over here as well. So if I show you, as you just have mentioned, so can you see the whole details over here in case of conv 2D?
Yes, sir,
What
yes,
sort
sir.
of arguments? So you can see, if I just scroll it, it will go. But there is a thing called kernel initialization. Kernel initializer, if you can see in the fourth
Yes,
line,
sir.
I guess 1, 2, 3, 4. Yeah, you go kernel initialization. So you can see that it supports string. So one such initializer is glodot uniform. Okay, so it uses its own probability distribution function to map the weight initializer values. So instead of, if you do not want to use glodot or he or uniform only or random, so you can create your own function and you can just pass it over there and it will do its job. Is it okay?
Yes, sir. Yes, sir. Thank you.
Okay, then you again do the upsampling part and then followed by the last decoding operation, which will give you the single channel image. So that is why you can see that only one filter we have used with 3 by 3, 3 by 3 kernel size, activation is sigmoid, and padding is same, and you feed the previous output to get the final decoded output. So again, I will not I think it is here. Okay, we have not defined conv2D, sorry. So we need to run this shell first and then this one. So now we can see that the layers have been instantiated. Let me just assemble all the layers and create an autoencoder. So this is the autoencoder. And let me show you the summary. So in my opinion, whenever you do deep learning, always try to visualize the model in terms of tensor values or the tensor representation. It will help you in understanding how the data is flowing into the model. So you can see that initially you fed a 28 by 28 by 1. Then after convolution, you get 28 by 28 by 32 as because we have 32 number of filters. Then you have max pooling. So max pooling is half. It is reducing the dimension by half. So 14 by 14. And 32 is the number of filters. Then again, you are doing the convolution operation. So there you get 14 by 14 by 32. Then you do max pooling again half. So 7 by 7 by 32. So in this way, you can see that we have done the and over from here, you can see that again the decoding part has been started. So you have 7 by 7 by 32. You start upsampling the data as 14 by 14 by 32. and then the process goes on, and at the end you get 28 by 28 by n1. So which was your initial input data dimension over there. And again, my suggestion will be to calculate these parameters by your own, considering the bias terms, and just re-verify whether you can calculate it by your own or not. So let me tell you, these are very easy things. Just get a pen and paper and start calculating all these values. So you will get a good grasp on the problem itself with this. And
So
again,
same way we have to
auto,
calculate, right? Parameters like input
yeah,
into
the
hidden
same,
layer.
yes, 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 the same way. Let me just show you over here where it is the MLP based autoencoder. So for example, over here, you in the input, you have 784 dimension, and let me go to the slide, so it will be easier. Uh, so let's say, so let's say you have an autoencoder like this 784, and this is the hidden layer. So you have 100 neurons over here, and at the output you have 784 layer 84 neurons again. So you need to write total number of parameters over here. So let me write it p1, and this is this as p2. So p1 will have 784 multiplied with 100, and as because now they are considering the bias term, so for each and every neuron will have an associated bias over there. So total number of neuron size in the hidden layer is 100, and for each and every neuron there will be one bias term. So how many bias terms will be there? 100 bias terms. So it will be 78400 plus 100, so 78500. So previously we guys have omitted this particular part, the bias terms, but over here, as because the Keras is computing the whole the weight term as well as the bias term, so we can actually incorporate the whole thing over here. So in the quiz questions, we just have bothered about this one. We just omitted this particular part. However, now as we are considering the bias terms, so this is the total 78500. So you can re-verify from over here as well. So let us just see. So you can see the total number of parameters in this particular layer is 78500. Okay. So in this way you can, and for the last layer as well, let me just show you the calculation. So over here, when you go to P2, it will be 784 into 100 again, but in this particular layer you have 784 neurons. So for each and every neuron you will be have an associated bias. So this will be 784. So it will be 78400 plus 784. So it will be 84, and it will be sorry. So it will be 197. So 79184. 79184. Let me just check. Yeah, 79184. Right. So this is how you can calculate the parameter. Is it okay?
Got it, sir. Thank you.
Okay. So over here you can see the summary, and again the same process. You can come first, you need to compile, and then you can train it for 100 epochs. So again, let me just omit the training part because it will unnecessarily kill time. So anyway, I will give you the code. You can run it by yourself. So after you do the what you call training the model, our main aim is basically to see that we are giving a noisy input, and we should get a clean output at the end. So here I am doing the same thing. So it basically displays the original data that we are inputting, and then it also gives you the reconstruction part. So that is what the model is basically generating from the noisy data. So in the input we are giving the noisy data, so that is why I'm plotting the noisy inputs, and at the output, so we'll be getting the encoded images. So you can just run at your end when I will share it in the GitHub. So it will be with all the data. So I have omitted this particular part because it will unnecessarily waste our time. So with this, the autoencoder part is completed. So let me just go to the LeNet part. Sorry.
Sir, this
So this is
GPU
the
and TPU, it matters, sir, while training
yeah,
the
yeah, yeah. Yes, 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 yes. It will substantially, it will create an effect. Let me in the LeNet part, I will show you initially with CPU, and then I will show you what happens with GPU. Okay. So you will see the training time will be increased in case of CPU because CPU does not allow the parallel processing, but GPU allows parallel processing. So what happens in GPU, for example, you are using 128 batch size and your machine is of 8 core machine. So this 128 number of data will be distributed in all the 8 cores. Now you can see in CPU, one by one, 128 data will go, all the computation will happen, loss will be calculated. In case of GPU, at once, 128 data will be distributed in all 8 cores. Parallelly, all computation will be done. Parallelly, loss computation will be done, and parallelly back propagation will be done. So you can, from intuition, you can observe that CPU will be very slow instead of using GPU.
Okay, sir.
Okay. So over here again, we need to import the library. So libraries such as NumPy, Matplotlib is for visualization. So sklearn, scikit-learn, we also have seen what is the use of scikit-learn. We'll be using scikit-learn for confusion matrix plotting. I will tell you what is confusion matrix later on. And TensorFlow we have imported, then MNIST data set from there, then sequential. So sequential is basically if you want to assemble all the layers in a sequential manner. So that means one by one if you just want to place them. So that is why we write sequential over there. Okay. Then you import the layers that you want, that is conv the average pooling, flatten and dense, and the categorical statement that is also required to encode the labels. So you know that from the MNIST data, first you need to generate the training and testing data. So that is what we are doing by using MNIST load. So not generating MNIST data package is basically contains all the data. You are just allowing them to come into train set and test set by defining these variables. Then we are rescaling all the values in between 0 to 1. So this sort of a normalization. And then we are reshaping the data as per the AlexNet dimension. So let me just show you what is the dimension. So if I just write dot shape, so it will add an extra dimension over there. So this is what it basically means, that you have 28 by 28 data. And as because AlexNet receives an single channel data to make the model understand that our data is a single channel data, so that is why we have appended an extra dummy dimension over there to just to let it know that our data is of single channel data. So this is 28 by 28, and we have expanded it to 28 by 28 by 1. Now here comes the LeNet architecture. So over here you can see I have given an image of LeNet. So in case of a LeNet, you can see that initially you have 6 filters, 6 filters, stride 1, padding 0. Then you have max pooling operations, 16 filters, and max filling operation. Then you flatten down, and then you have few fully connected layers, and at the output you have softmax based class dependent probabilities. So over here you can see the model equal to sequential. So you can define your model like this as well. So model equal to sequential on 2D. 6 means number of filter is 6, kernel size is 5 by 5, activation is ReLU, and you can define the input shape over here. So in previous cases, I was writing input shape separately, but over here I have written input shape. I am trying to write the input shape as well within the sequential layer itself. So there are plenty of variations you will see while defining the model layers and all. So you can use any sort of convention. So just to illustrate to you that this is, you don't have to stick it to any sort of single representation. You can use different representation to create your neural network architecture. So for example, either you can instantiate the input shape outside using an input layer. Otherwise, in the convolution layer itself, you can declare the input size like this. After that, you have a pooling layer. So we are using average pooling 2 by 2. Okay. Then again, a convolution layer with 16 filters, kernel size is 5 by 5, and activation is ReLU. Then we are using the average pooling layer. After that, we need to feed the data into the dense layer. So dense layer receives one-dimensional data. So flatten, what it will do, I have already shown you. From a two-dimensional data, if you use flatten, it will give you 1D data. So therefore, this flatten layer will create a 1D data, and then you can feed this flattened data into a dense layer of 120 neuron, then 84 neuron, and our final classification task is of 10 class classification, because image data comprises either from 0 to 9 digits. So therefore, you have total 10 classes. So we'll be using 10 class classification, and activation is softmax.
Sir,
And now we can, yes, please.
Sir, AlexNet and LeNet both are different architectures, right?
Yeah, both are different
Then
architectures.
are we doing comparisons here, or how it is, sir?
Actually, what happens is basically they had a problem called large scale image classification using ImageNet database. So that problem, initially when this problem came, people came with different solutions. So each and every year there was a workshop or a conference was there, that was called CVPR. In CVPR they had that challenge. So every year people used to come with their own architecture, and they showed that we got this much of accuracy increment. We got this much of accuracy increment. So over here, I'm for the illustration, I'm just showing the LeNet architecture. However, as you can see that how I have written the LeNet architecture, you can re-simulate the AlexNet, VGGNet, etc. So this is just to show that how to write the CNN by your own. And anyway, in your application, as far as research is being concerned, so generally we do not reuse those networks, because those networks have their own drawbacks. For example, AlexNet, it has 60 million of parameters. So to train a AlexNet, it is very difficult to train in our machine, because we do not have that much of compute resource. Okay, so uh, the main funda is that you try to get it down that how to write a CNN by your own, then you write your own custom CNN, and you show that what is the performance. So as far as course is concerned, we'll be sticking to the um, textbook versions of the neural networks like AlexNet, LeNet, and all. But in real life, we do not use those previously simulated architectures. For transfer learning, we use them, but in your particular application, what you can do, you can write your own CNN, do the classification, do the regression, whatever job is you are having. You do your deep learning done with your particular written down convolution neural network, and then you can show the performance comparison. However, I'm not doing the performance comparison with LeNet5 and AlexNet and all. I'm just showing you that how to write the CNN and how to train it.
Okay, sir.
So over here, you can see that model summary. So you can see that this is the first convolution layer output, as because we have 6 filters. So the output is a 6, the channel number is 6. Then we are using average pooling. So average pooling, what it will do, it will create the half, the dimension will be reduced to half, to 12 by 12. Only the spatial dimension, not the channel wise dimension. Then we are using the convolution layer again, and we have 16 such filters. So output is 8 cross 8 cross 16. And average pooling layer, we are using it in the subsequent layer. So the spatial dimension will be reduced to half. So we can see that 8 by 8 is reduced to 4 by 4. Now the flatten layer. Now the flatten layer, what it does is basically it creates a one-dimensional data. So you can see that from 4 by 4 by 16, you are getting 256. If you multiply all these dimensions, you will get 256. That means it has, from this tensor, it has just created a one-dimensional data out of the whole tensor. So 256 is the output. Then you feed it to the 128 dimension, 120 dimensional dense layer, followed by 84 dense layer, 84 neuron dense layer, and at the last we have 10 10 output neurons, and these output neurons are activated using softmax function to give you the class probabilities. And in the right hand side, you can see again the parameters have been written over here. You can calculate the parameters by yourself to get to know that how many total number of parameters you are having. And total number of trainable parameters is 44,426 for your application, basically. In case of ImageNet classification, they had 1,000 classes. So you can see that instead of 10, you have to write 1,000 over there. So the LeNet5, original LeNet5 will be of much higher trainable parameter. However, as because our problem is of only 10 class classification, that is why trainable parameter is further reduced. And as because I will not be able to train the network on ImageNet database, obviously, because ImageNet database contains 10 millions of data. And this Google Chrome will be it will not be able to train the 10 million of data on Google Colab. So you need to have very large amount of space over there to train the whole model and to store the images as well. So in Google Colab, you will not be able to do that. Okay. And if I just tell you the LeNet, it took a 1 week itself to train on 10 millions of data. So you can understand that how much compute resource you have to do these sort of simulations over there for ImageNet database at least. Okay. Now we need to, now the process is just like the previous one. So we need to compile the model. So we have used Atom Optimizer. Loss is categorical cross entropy. So we all know that what categorical cross entropy is. And for multi-class classification only, we use categorical cross entropy. For binary classification, so we use binary cross entropy. And the metric is accuracy. So obviously we'll be checking the accuracy, that how well we are classifying the data. And thereafter, this is the history. So history will save all the training accuracy, validation accuracy, training loss, and validation loss. So that means you need to train the model. So to train a model, we need to write model.fit, and it will take the training data, table, number of epoch is 10, batch size is 128, and validation split. So it will split the training data into 20% validation data to validate the model. So I think I can train this model as because the epoch is 10. So I think I have to change my runtime. Yes, as you told that what is the effect on CPU. So let me change it to CPU first and then show you that how much time it takes. So I need to rerun these cells again. Okay, so let me just run this one. Yeah. So I can delete this one. So this is the model. And now let me train the model. So the performance will not be affected. CPU and GPU, it basically helps in reducing the training time. Sorry, GPU helps in reducing the training time. Its job is to efficiently do the computation process. Otherwise, if you train a model in CPU, let's say you are getting 96% accuracy, GPU, after training it on GPU, it will not give you 98% accuracy. The accuracy will be more or less same, but the thing is that GPU will give you the faster training. So over here, you can see that 1 minute 13 seconds for only 7 iterations. Okay.
Sir,
So
during
probably it will
training,
take
internet speed matters, sir, or it will be in backend it will work,
Ah,
sir, the training process?
okay. So as because you are running this on Google Colab, so this is a web-based platform. So whenever you will be disconnected with the internet, this all process will be vanished. So you need to retrain it again. But if you are running this deep learning model in your hardware itself, for example, if you are using Anaconda, so then you don't have to bother about the internet connection and all. However, Google Colab is purely a web-based solution. So you can see that if you are not having internet, so you will not be able to go to the website first. So that means if you are getting disconnected with the internet, so then and then your training process and everything will be stopped. But if you are using Anaconda, in Anaconda, these problems are not there. You don't have to bother about internet and all because you are basically running all the model, all the computation into your hardware itself. So in case of Anaconda, you don't have to bother about it. However, in case of Google Colab, as because you are using a browser over here, so it will be disconnected if you are not having sufficient internet.
But sir, on Anaconda, the GPU option we will not get, no? Only on CPU it is.
No. You are in Anaconda, you will get GPU. If you're it basically uses your laptop or your system. If your system is having GPU, so from the properties of the my computer, or you will get to know for or let's say if I show you, go to go to task manager. I think in this particular machine I don't have GPU. So go to performance. Yeah, so you can see that I have CPU only. This is memory, this is disk space. We have an SSD over here, and this GPU is not that GPU I'm referring to. So this is basically an inbuilt GPU for doing a basic graphic operation. If you have a dedicated GPU, like for example NVIDIA RTX something, RTX 400 or something, so that GPU is for gaming purpose. So we can exploit that GPU that is there in the system using Anaconda. So for that, uh, you can install this particular software, or this particular package is called CUDA. So if you have it will work with NVIDIA GPU. Okay, so if you have an NVIDIA GPU into your laptop, and if you are using Anaconda over there, then you can install CUDA, and this CUDA will help you in driving your GPU. So you can use the GPU there. because Anaconda basically works on your particular hardware. However, Google Colab gives you the cloud-based GPU. It has a server, and in the server you have a cloud GPU, and it allocates a place for you. And in Anaconda, it allocates all the place based on your system hardware. So you will see if your system is not that great, Anaconda will take so much of time to run one sort of code. So you can use GPU using Anaconda as well, but you need to first assure that you have a GPU installed in your system. Install means you have a GPU over there in the system, and you can write that GPU using CUDA. So for CUDA, you have different distributions like CUDNN and extra, etc. You can search it on internet, and from there you can download those particular software patches, and then you can use Anaconda to drive your GPU and train the model on GPU itself. So that is on system GPU.
Okay, sir. Thank you.
Okay. So we took 2 minutes 23 seconds over here. So substantially, if I just show you the plot of the curve, so you can see we are getting good amount of accuracy and loss is also decreasing. Now let us just show you the test result. So at the test time, we can see that test accuracy is 98%, 98.62%. That means we are getting quite a good accuracy within just 10 epochs only. But this is for MNIST dataset. In any real data set, real-time data set, if you acquire, let's say my research area is biomedical signal processing, hardly you will get very nice data on which you train a deep learning model, and then and there you will get a 98% accuracy, because that is very hard to achieve. This particular data set is a hello world problem of deep learning. So in any coding language, whenever you start writing the code, first thing what you do, you print a hello world. So MNIST dataset is a hello world problem for deep learning. So in this particular dataset, you will get very good accuracies, even with 10 epoch, 5 epoch, 20 epoch. But in case of any real data, it is very hard to achieve. So there basically comes the novelty of the problem, that how you have achieved that certain amount of accuracy. So we can leave that part apart. So this is confusion matrix. Confusion matrix is basically you have 10 such classes. You will be predicting, you have the true level, you are predicting the image using your deep learning model. So let's say you have 10 images of class 0, and your model is predicting 9 images correctly. So that means you have a misclassification of 1. So over here we are showing the same. That means this is the 0th class. So at 0th class, we can see that 973 images have been correctly classified, but these images are incorrectly classified to other classes. So if I show you in a better form, it is like, yes. So you can see that this is the 0th class. So then in the upper axis also, this is 0, 1, 2, like that. So this 0, total number of 973 images have been correctly classified as 0. But this particular 2 images have been correctly to class 9, let's say. Similarly, over here, it belongs to 1126 images have been correctly classified, but these images have been miscorrectly classified to other classes. So this is what is basically meant by a confusion matrix. So that means how much confusion you have while doing the classification. So for each and every class, you can see that there is some sort of confusion. For example, in case of 9, you can see that 993 number of images have been correctly classified, but 3 of the images which belongs to class 9 but predicted as class 7. So that means you are doing some misclassification there. Okay. Now this is just to show the visualization of the test result. So I think I have to just zoom it out a bit to show it to you. So over here, what I am doing is I am feeding this particular image into the trained model, So I know that what is the original level. That original level is class 0, and the predicted level, that means what the model predicts, what my LeNet predict. So that is basically 0. So that means we are doing correct classification. And if I show you for the first 100 images, so it will be like this. We'll just take a few moments to calculate, and then we can see that a 10 by 10 grid. So yes, now you can see, so this is a 9, original is 9, prediction is also 9. This is a 6, that means original is 6, prediction is also 6. Original is 3, prediction is also 3. So likewise, you can re-verify everything. For example, this is a 0, original level is 0, and your model is also predicting it as 0. So now we can see that, okay, for each and every result, we are getting the correct classification. Now, where we are doing the misclassification. So to visualize the misclassification, I have written this particular snippet, which will basically show that where it basically does the confusion part. For example, this thing is quite confusing. It is actually true. A true one is basically 4. That means original level is 4, but it is predicted as 9, because some of us write 9 like this also. Okay. So for example, over here, this is 2, but it has some similarity with 7 as well. So in this particular image, you can see that this is a true level is 5, but model is confused with the prediction 3 because it has some similarity with 3. Over here, another prominent problem. The true level is 6, but the model has predicted 0, because you can see that it is very hard to predict that it is either it is a 0 or 6, isn't it? Same thing, some other mishaps are also there. So this is 8, but model is confused between 0 and something. This is 3, 2 is 3, but the model is predicting it as 5. So you can manually check, or you can write a code like this to generate to see all the misclassifications there. So with this, we have implemented the LeNet architecture. We have implemented 3 different variety of autoencoders. So one is shallow autoencoder, deep autoencoder, and convolutional autoencoder. So I'll be sharing all these uh, code snippets with you in my GitHub account. So you will get it shortly. So after this, let me just go to the questions for week 8. So over here, if you have any further questions regarding the coding, you can ask me. Otherwise, I will proceed with the practice questions. Any questions on this particular aspect?
Hello, sir.
Yes.
Hello. Sir, my name is Harshini, sir.
Yes.
Hi, sir. Sir, my research work is on image registration.
Okay.
Hello. So for image registration, if you are having any ideas sir, regarding that image registration, like satellite images are taken from 2 types of sensors.
Okay.
SAR sensor and optical sensor. So I want to do the registration between that type of images.
What do you mean by registration?
Registration means I can say that, like what are the differences, like because satellite images as it is taken 360 in 360-degree angle, and it will be continuously taken. Okay. So I want to know about what is the difference between the two images, means at time t1 what was the image, time t2 what was the image, like that only. The difference between the image taken with optical, that is sunlight, the image without that is taken without sunlight.
Okay, so the
Yes.
one very prominent application would be, for example, if you have two different classes of data, let's say this green one is satellite one and another one, what you told?
It is
So two
satellite
different
only, sir. Two
sensors you
also
said. Two,
sensors, yes, sir.
two different
Sensors.
sensors. So this is sensor one
Yes, sir.
image and this is sensor two image, right?
Sensor
So
to
you
image,
want
yes.
to know
Yes,
you want to know the difference between these two. Okay, so
these two.
you can refer to one of my paper. So what was the main idea? So for example, if you have two different images, let's say uh, you have a kid and you have two different colors, two different set of balls. One is red ball and one is black ball, and
Okay, sir.
all of them are mixed into a container. Now, if you tell that particular boy to separate them out, so for example, initially you told that, okay, so this ball is a black ball and this one is a red ball.
Yes.
So you have shown that how the black ball and red ball looks like, and then you ask
Yes.
that guy to separate it out. Now, as because he
Yes.
has seen that this is a black one, this is a red one, in his mind, he has gathered some features, and now when he has seen these two images, now it will be able to, in his mind, he has certain features for black ball. He has some features in his mind for red ball. Now what he will do, one by one, he will collect all the black balls into a bucket and all the red balls into a bucket. So that means he has learned, while showing these particular images, the balls, he has learned some distinct features from these two set of balls. So
Yes, sir.
learning the distinct feature in your application will actually tell you that what is the difference between S1 and S2. As because this
Yes.
guy has he has learned some feature for these two different classes. That means he knows that, okay, if I see a black ball, I I will get these sort of features. If I receive these sort of features, that means this is a black ball. I will separate it out to a another container. If I see a red ball over here, I will in his mind some features will come. Okay, if these features are coming, that means I have to separate it out into another container. So in your case also, you have two set of images. Now you need to learn two different sort of features out of these two images, which will tell you that what is the difference between S1 and S2. So for
Yes,
that,
yes.
what we do is actually, so I hope I have given you the intuition. What is the intuition?
Okay, sir.
So no, I'm just telling you that have you got the intuition from this particular example that how
Yes, sir. I understood. I understood
okay.
how
So
it can
now what
be.
you will do, how it can be done is basically you train a parallel model, three parallel models. So in
Okay,
one
sir.
parallel model, it will take the positive. So there will be three classes: positive, anchor, and negative. I can refer you one paper that is
Okay, sir.
triplet loss. You can see.
Triplet loss.
So
Okay.
for example, yeah, triplet loss. So for example, in your case, let's say you have this S1 image. So
Yes.
positive means from the same class, another data comes from the same class. This is S1,
Okay.
this is S1 positive, and negative means from the other class the data comes. Okay, so this is S2
Okay.
data. Now you
Okay.
feed this data to the model, each and every model. So
Okay.
this model this model will produce a feature, so as all these models will produce the features. So this is another feature, and this is another set of features. Okay, so now as you can see that these two data are coming from the same class. That means sensor 1 class से ये दो आ रहे हैं. So as because
Yes.
these two data are coming from the same class, these two features will be very alike, right? And you can see that these two data are coming from two different class, so their feature will be very different.
Very different. Yes.
So what
yes,
will
sir.
happen? What will happen in the feature space? All your data from sensor 1 class will be clustered like this, as because you are imposing that they will have similar features, and
Okay, sir.
the sensor 2 data, as because you are imposing that sensor 1 data and sensor 2 data, they are coming from two different class, so they will have very different features. So you can see that in between the sensor 2 data there will be very compact information. However, in between sensor 1 and sensor 2 data, you'll see substantial gap is there. Okay, so by which you can ensure that sensor 2 has these features and sensor 2 has these features, and when you uh, take a difference between, let's say this is sensor 1 data and this is sensor 2 feature only. So if you take difference between feature 1 and feature 2, then you will see that huge gap will be produced, and from there you can get to know that what is the difference between these two features.
Okay, sir.
So you can see triplet loss, and another paper is there. This is asthma SCEL net. So you can go to my Google Scholar. From there you can get this paper, and this is publicly available. So you can refer to that paper.
Okay, sir.
Okay.
Sir, another thing.
Yes.
Sir, if GPU is not available in our laptops.
Okay, so then you can use Google Colab, because in Google Colab you will get GPU.
Okay. So while if we want to showcase the results also, we can by using Google Colab only, I can show the results.
Yes. By Google Colab only you can show the results.
Okay. Okay, sir. Thank you, sir. Thank you.
Yeah. So let me just scheme you through the problems. These are very simple problems. So you have an image dimension 257 cross 257 cross 3. You have kernel of 7 cross 7 cross 3, stride 2, and padding 3 using a 2D convolution. So what will be the output size? So output size is equals to input size minus kernel plus 2 into padding. So these are formula based questions. So divided by stride plus 1. So you have 257 as input dimension, your kernel dimension is 7, plus padding is how much? Padding is 3. So this is 6, and stride is 2 plus 1. So it will be 256 divided by 2 plus 1. So it will be 129. So you'll have 129 cross 129 cross 1. So this is your final answer for this particular question. Okay. So the second question states that what is the primary reason for adding pooling layers? So pooling layer, what it basically does is it reduces the dimension. So reduces dimension. Reduces dimension means in subsequent layer, the computational complexity will be reduced. Computation complexity will be reduced. So let us just scan it through. It promotes small shift in variance. So in recent years, so there are some papers. So one is probably blue blood. So you can refer to this paper. So they have showed that pooling layers, they do not basically provide much shift in variance property. So you can omit this particular option. Because see, anyway, in deep learning, the deep learning thing came a decade back. So there are several things which are also under research. So day by day, if you see the paper, you will see new things are coming up. So initially, people said that a pooling layer gives you shift in variance, but later on, with several problems, people found that they do not provide much shift in variance. So all these things are basically still under research. So I would recommend you to omit this particular option because of this particular paper. Okay. After that, it reduces the computation. This is true in the subsequent layer, and it provides to produce activation, summarize, filter response in local windows. Obviously, because let's say if you have a output like this, and you are taking pooling operations from the subsequent patches. So what it does is basically within a local window, it, for example, you are doing average pooling. So in local window, it will take an average value like this. For example, it will put an average value over here. Then from this particular layer, it will put an average value over here. So for the local window, it gives you the summary of the filter. So option C is also correct. So both B and C are the correct options. So you need to choose option D over here. Okay. So this particular question says that suppose you have 8 convolutional kernel with 5 cross 5 dimension, no padding, stride 1, first layer of convolutional neural network. In the first layer of convolutional neural network, you pass an image of 228 cross 228 cross 3 through this layer, and then what will be the dimension of the data that you receive. So let me just write this whole thing in a schematic manner. You have an input. So this is your input image, and you have 5 cross 5 filters. And how many such filters? 8 such filters. And stride is 1, padding is 0. And what is the output size that you will get? So spatial dimension will be 228 minus kernel size is 5 plus 2 into padding, that is 2 into 0, divided by stride is 1 and plus 1. So it will be 2 to 3 plus 1, it will be 2 to 4. That means your spatial dimension will be 2 to 4 cross 2 to 4. And what will be the channel size? What will be the channel size for this particular output? Is anyone? Output channel size is equals to number of filters applied. Number of filters applied. So over here you can see the number of filter is 8 from this particular 8 convolutional kernel. So number of filter applied over here is 8. So the output will be 224 cross 224 cross 8. So option B is the correct option. Okay. Then a question on transfer learning. So transfer learning, in case of a transfer learning, you have a bigger model. So let's say VGG16. So what you do for your case, VGG model is trained on ImageNet, and it does 1000 class classification. In your particular case, what you do, you take the initial layers, you chop off the last layer, and you reinitialize your own dense layer and do the classification on a smaller data set. Let's say an Pascal data set, which has very small, very limited number of images. ImageNet had 10 millions of data. It has, let's say, 10K of data. That means 10,000 data. So you are using the VGGNet initial weights and then you are fine tuning. So this process is called fine tuning. So you will see all these things in the lectures as well. So let us now scan it. Higher layer learns the task specific feature. So this is false because higher layer means these layer, these sorry. So higher layer means the last layer. So you have seen that in the initial layers it learns the edges, and when you go to the last layer it learns the face, it learns the emotion like this. So higher layers are task specific features, whereas the lower layers learn general features. So general features like age, like vertical lines, horizontal lines, like that. So option A is correct one. Then you have transfer learning is generally used in a situation when task specific dataset is very less. So I have also shown that your task specific dataset is very less than the source dataset. Source dataset had 10 millions of images. Now Pascal has only 10K images. So over here, option D is also correct. So option C is the weights of lower layers of pre-trained CNN trained on dataset like ImageNet, etc. are copied. So the weights of lower layer of the pre-trained network. So this is a pre-trained VGG, and the lower layer weights have been copied over here, and then higher layers are randomly initialized. So I have created the higher layers by my own and which are randomly initialized using Gaussian initializer, and then the entire network is fine-tuned. So already I have said that this mechanism of retraining this particular model is called the fine-tune. So option C is also correct. So over there, option D is the final answer because all of these above are correct options. Okay. So next question is, what is the advantage of ReLU over sigmoid and tanh? So sigmoid and tanh, they basically look like this. So this is sigmoid, which saturates at 1, and over here the value is 0. And in case of tanh basically ranges from +1 to -1. So over here you can see when it reaches to the higher value in the positive direction and in the negative direction, the curve basically saturates. Now, if you take the gradient over here or the tangent over here, you can see that very less change will be there. That means the gradient will be almost very smooth and could be very less variation, which basically arises the problem of gradient vanishing. Because you can see that very less changes are there in the gradient. So very less changes means approximately equals to 0. So that therefore, if the gradient is very slow over there, so it will arise a problem of vanishing gradient over there. So, however, in case of ReLU is of this sort behavior. So you can see that over here the gradient will be 1. So wherever you go, if you do the dy by dx, it will be 1 only because y is equals to maximum 0 comma x. So for x greater than 0, so y will be equal to x and dy by dx will always be equal to 1. So over there you can see that there is no sort of vanishing gradient problem is there. So let us now scan through the options. So advantage of ReLU is sigmoid tanh. Option A is low computational requirements. So obviously you can see that less computational requirement is there. However, in case of sigmoid, if sigma of x is there, if you do the gradient sigma dash of x, it will be sigma of x 1 minus sigma of x. So it takes quite amount of computational resource to calculate the sigma x value and 1 minus sigma x value. However, over here you can see that the gradient value is fixed 1. So therefore, you can use a single hardware or single marks or single multiplier over there to implement this particular operation over there. After that, so it helps in low computational complexity. It alleviates the vanishing gradient to some extent. Obviously, we have shown that it actually alleviates the vanishing gradient problem. Okay, and backpropagation is simpler because in case of backpropagation, you need to take the derivative of the activation function. So in case of sigmoid, you can see that activation function derivative is quite a big term. However, over here you can see that dy by dx will be always be 1. So backpropagation is quite simpler in case of ReLU. So all these options are correct. So option D is the final answer for this particular question. Okay, so the next question states that again it is for transfer learning. So in case of transfer learning, the lower layers are more generally transferred to another task. Statement 1. For the transfer learning task, last few layers are more generally transferred to another task. So can any one of you tell me that which of the statement is correct one? Yes, anyone? Okay, so in case of transfer learning, so TF learning, so these are the initial layers or the lower layers. So lower layers basically learn the general features like edges, vertical lines, horizontal lines. However, in the higher layers, they basically learn the task specific operation. For example, you will see the face will be generated, emotion will be reflected. So we don't need the task specific layer. However, we need the lower layer that basically learns the general features. General features. So therefore, let us see transfer learning task. Lower layers are more generally transferred. Yes, we are transferring the lower layer to another task. So yes, option 1 is correct. Statement 1 is okay. Now for transfer learning, last few layers are more generally transferred to another task. So we are not doing the last, we are not transferring the last layers. We can see that we are chopping off. So we are inferring only the lower layer. So statement 2 is incorrect. So let us see. Statement 1 is correct and statement 2 is incorrect. So over here, option A is the correct answer. Okay. So the next question states that adding more hidden layers will solve vanishing gradient problem for a two-layer neural network. So if you have a neural network like this, if you add more layers over here, so this number of layer in the deep learning model, if you increase, vanishing gradient problem will increase. So this line is totally contradicting with our knowledge, because they are saying adding more hidden layers will solve vanishing gradient. It will not solve. It will even arise to a problem of vanishing gradient, because if you have more and more number of layers, and you have used the sigmoid activation function over here. So everywhere it will be multiplied sigma x 1 minus sigma x, and these values are almost less than equal to 1. Let's say the maximum value is 1 upon 4. So you can see that the multiplication value, if you increase the number of layers, this will the output will even further reduce. So if, for example, 1 by 4, 1 by 4 like that, if you multiply, even it will go less than it will be approximately equal to 0. So therefore, the vanishing gradient problem will be arise in case of higher, if you increase the number of layers. So vanishing gradient problem will be prominent over there. In case of statement 2, making the network deeper will increase the chance of vanishing gradient. Yes, that is what we are talking about. If you increase the number of layers, hidden layers, it will increase the problem of vanishing gradient. So statement 2 is correct. So yes, statement 2 is correct. Okay. So the last, this is probably the last question is, so in the last question, so the question is how many convolution layers are there in LeNet5 architecture? We already have implemented the LeNet5 architecture. So we had 2 convolution layers over here. So this one is the convolution layer. This is con. This is pooling. This is again a conv layer. And this is a pooling layer. This is a flattened layer. This is a dense layer. This is the classification layer. So we can see that we have only 2 convolution layers. So option A will be the final answer for this particular question.
Sir,
So if you have any, yes.
Flatten means what, sir?
Flatten means, for example, you have a data like this. Let's say the dimension is 2 cross 2, and let's say you have 3 such channels. So your data is 2 by 2 by 3. That means m cross n cross, let's say z. So this is called a tensor. Now your dense layer does not support tensor. It supports 1D data. Now from this 3-dimensional data, first we need to get a 1-dimensional data. How will you get? So you can get a 1-dimensional data like this. So total number of elements, how much elements you have over here in this whole tensor, that is 2 to the 4, 4 3 is the 12. So you have total 12 number of parameters. So this particular tensor, if it goes to this flattened layer, the flattened layer will give you a dimension that is 12 cross 1. So now you can see from this 3-dimensional data, now you are getting a 1D data. So this is the job of the flattened layer. It basically flattens the whole data into a 1D format. So if you have, let's say, a data dimension like 5 cross 5 cross 10, the flattened layer, what it will does is it will create a 1D vector of size 250 cross 1.
Okay, so the difference between flatten and dense.
Okay, difference between flatten and dense is basically it links the tensor. Previously it was a tensor. Your tensor cannot go to dense. So this flatten layer basically links this tensor to 1D data. Have you got the point? So over here in this particular layer, your data shape, let's say it was 3 cross 3 cross 10, but your dense layer is of shape, let's say 120 cross 1. So anyway, you can see that your data dimension is 3-dimensional data, and in case of the dense layer, you have 1D data. So how you will fit this data into the dense layer? Data dimension or the data type should be similar. You cannot feed a 3D data into a 1D data. Is it possible? So you need to get a 1D representation. You need to get a 1D representation from this particular data. So how will you get this 1D representation? This is by flattening the data, and you will from flattening you will get data shape like 3 3 is a 9, that means 90. So it is 90 cross 1. So at the flatten, the dimension is 90 cross 1. So now you can see that from this tensor data, you got a 1D vector. Now this vector can communicate with the dense layer, because dense layer also is 1D. So data, to make the data dimension uniform, to feed it to the dense layer, we use the flatten layer.
Okay, sir. Thank you, sir.
Okay, so if you have any further queries, then I can take, otherwise we'll end the meeting here. Any query?
Sir, what is the direct delta function?
That is an impulse function. If you are from, so direct delta is like this. Let's say this index is n, it is sigma of n. This is in case of discrete case. If you have some background in digital signal processing, then it is like 1 at n equals to 0. So at n equals to 0, the function will exist, and elsewhere it is 0 only. So this is how the delta Dirac looks like. So this is called delta Dirac. It is also called, I am not able to recall the correct spelling, but it is also called Kronecker delta, or it is also called impulse function. So in time domain, you can write the same thing, delta t. So this is the function of delta or delta data.
Okay,
So it comes
sir,
with
where this
system
will be helpful, sir,
information.
in our deep learning? As an activation function, these are used?
No. Nobody uses delta direct. Delta direct probably it comes when people talk about convolution and all, because this convolution thing, it was there in DSP first, and then it came to this deep learning. So while trying to map it from DSP to deep learning, we need some filter response, then system transfer function, all these things are there. So we might refer to because let's say you are doing convolution. So this h of n is basically generated from the you can get some information from the system impulse response or the delta direct information from the systems transfer function. So that is why in case of convolution neural network, people may talk about this delta function, direct function, etc. But these are actually they are in DSP, but from DSP this convolution thing came into deep learning, and that is why to link up these things in for giving you some intuition, people talk about this delta function. Otherwise, you do not need delta function as such in deep learning application. Nobody uses these as what you call as activation function and all.
Okay, sir.
Okay. Okay. So let me stop recording.